Welcome to Lecture 9 for Chemistry 141. So we finished off the last lecture talking about p orbitals, and so we want to talk about d orbitals here. And d orbitals have an L value equal to 2, and these start when you have an n equal to 3. And so your d orbitals start with a 3d and then goes on to 4d and 5d. There's no such thing as a 1d orbital or a 2d orbital. Now each level has 5 d orbitals, and this is because you remember your m sub l goes from minus L to plus L, and since L is 2, we get m sub L values of minus 2, minus 1, 0, plus 1, and plus 2. So 4 of the orbitals have a similar shape, and they have a cloverleaf shape that has 4 lobes and 2 planal nodes that goes between the lobes. And 3 of them are in planes between the axes, and these are the dxy, the dxz, and the dyz. So those are oriented in the planes bearing the letters of their name. And then the dx squared minus y squared is oriented directly along the x and y axes. And then we have the dz squared, which is a little bit of an anomaly, but it's just what the math bears out. And it looks like a pz orbital with a donut around it. And so some of these can be hard to envision without seeing pictures. So let's take a look at some pictures of the d orbitals here. And so there we have a dyz orbital there, and it's got its lobes in the yz plane. We've got a dxy orbital here, and it's kind of hard to see, but its lobes are in the xy plane. You can see that the lobes themselves pass between the x and y axes. They don't actually lie on the axes. And then we have a dxz orbital, which is very similar to the yz and the xy. It just happens to lie in the plane of the x and z axes. And again, the lobes there go between the axes. They don't actually lie on the axes. Our dx squared minus y squared orbital here is also a cloverleaf shape, but this one has its lobes directly on the axes. So it's in the xy plane, but its lobes are directly on the axes. And then our real strange guy here, our dz squared orbital. As you can see, it looks like a p orbital, pz orbital, because those orbitals are aligned on the z-axis, and then in the xy plane there, we've got this donut shape that goes around it, and within that donut, it is empty. There is a nodal plane that goes around that donut. So strange shapes, we'll focus more on those much later in the course, maybe not even till we get to Chemistry 143. But the shapes are really interesting, and these are just borne out by math. So these are the maps of the electron probability as dictated by the solution to the Schrodinger equation. So we really start looking at the periodic table. It's an icon of chemistry. We look at the periodic table. It has a very iconic shape, and the shape really does mean something. And we're going to explore a little bit about what all of that means eventually. But let's kind of take a look and see how all of this was developed. If you look at the 1800s, up until then, there was maybe 20 or so elements known, and everything that we knew about chemistry was made with those 20 or so elements. And then the 1800s hit, and people were just driven by a search for new elements. And so during about the first half of the 1800s, they found about another 50 elements going. So by about 1860, we had about 70 elements found. And so now it became a bigger task to try to organize all of these elements and really categorize the elements both by behavior, chemical behavior, and chemical properties. And a lot of different chemists looked at arranging them in particular ways, but the one with whom we credit the most successful endeavor here is a Russian gentleman by the name of Dmitri Mendeleev. And so he began to sort the elements by chemical properties and by chemical behaviors. And when he did this, he started seeing patterns that began to form in chemical reactivity. And so once he started looking at the chemical reactivity and arranging the elements by atomic mass, he saw that the chemical properties repeated on a regular basis, so either every 2 or every 8. And then as he started getting into larger elements, started going every 18 and every 32. So he started seeing this repeating behavior, and this is what we call periodicity, and that leads to this concept of periodic properties. When something is periodic, then it repeats. That's what the term means. So the elements got arranged in a table according to mass and properties. And in order to refer to them, we have a couple of terms that we use. The rows in the periodic table we call periods, and the columns we call groups. Now we refer to groups much more often than we refer to periods. What we'll see with the groups is that elements within a group, so within a column on the periodic table, tend to have very similar reactivities and similar chemistry with the same elements. We also have down at the bottom what we call lanthanides and actinides, and sometimes you'll see a periodic table that actually has them included in the main table, but more often than not they are extracted from the main table and put underneath. So those are the lanthanides and the actinides. We don't do very much with them in this class. And once we put all that together, we get our periodic table. And we can just take a look to see what that looks like. If you've had chemistry before, you're very familiar with the periodic table. We see a couple of different features on here. We've got some names of our elements. So we've got the yellow blocks here, which we refer to as main group elements. And these are the ones that Mendeleev was working with primarily. And then we've got the transition elements here in blue. We usually refer to them as transition metals. And then we've got our guys down here. We've got the lanthanides and the actinides here. And they usually fit in up there if they're going to be put into the periodic table. The other thing it does graphically is it really makes that periodic table really wide. We do see a couple of different ways of looking at the group numbers here. We've got group 1, 2, 3, 4, 5, 6, etc. up to 18. And that's kind of a newer way of naming the groups there. I prefer to use the older way, and you'll hear me refer to those. So we've got our A groups and our B groups. And we really like to refer to the A groups. So we have group 1A, group 2A, group 3A, 4A, 5A, 6A, 7A, and 8A. As we start to get into making compounds, the reason I like to use those that older naming convention will become more evident. Let's go back to the atom here and see how we started filling in our electrons into our atoms and getting everything to agree with the periodic table as far as their periodic properties and their chemical reactivity. So we talked a little bit about this concept of electron spin. We looked at that spin quantum number. And electron spin was first observed in 1921 by splitting a beam of hydrogen atoms with a magnetic field. Now, a hydrogen atom has only one electron on it, and what they noticed is that the beam would pass through a magnetic field and would deflect in two different ways, and these two different ways were of opposite directions. And so it became evident that that there must be two different spins to create those two different or those opposite deflections when passing through a magnetic field. The electron on that hydrogen is charged and it's spinning, and that gives it a magnetic field, and that magnetic field is dependent on the direction of the spin, and that's what controls which way a hydrogen atom is going to deflect within a beam. And we can take a look at a picture of that experiment here. So we've got our beam of electrons. It kind of scatters as it comes out of that, but then it gets focused into a single beam. It comes through, and then depending on the direction of the spin of the one electron, one is repelled away from the South Pole and attracted to the North Pole, and that would be our minus 1/2. And then our plus 1/2 has just the opposite behavior. It's not important for you to know that the minus 1/2 is attracted to the north and the plus 1/2 is attracted to the south. The only thing you really need to take away from the diagram here is that the plus 1/2 spin and the minus 1/2 spin are opposite and get deflected differently when applied to a magnetic field. So this idea of electron spin helped us arrange our electrons in our orbitals using things called electron configurations or orbital diagrams. And we're going to just have a brief introduction to those in this lecture. We'll start expanding those to much larger atoms in the next lecture. But let's take a look and see what an electron configuration looks like. So here we have, for a hydrogen atom, the first orbital that's going to fill in is going to be the 1s orbital because it's the lowest in energy. And then we say how many electrons are in that 1s orbital. Well, hydrogen only has one orbital or one electron, so it's going to go with the little 1 right there. So we say that as 1s1. Now we can also use what's called an orbital diagram. And in an orbital diagram, each of our subshells, so in this case the 1s, is labeled, and each orbital within that subshell is noted either by a square or a line. And so we can take a look to see what hydrogen would look like here. And there we see our 1s orbital as a square, and our electron here is drawn as a one-headed arrow or a half-headed arrow. That's usually how we have electrons in these diagrams. And so this would be an example of a spin-up electron. We could have just as easily put it in as a spin-down. That would also be correct. It's more convention to put the spin-up in first, and then if you have to pair them up, then you put in a spin-down, but it doesn't really matter. Now, Wolfgang Pauli started looking at the idea of how electrons are going to go in, and he has what he's called the exclusion principle, or the Pauli exclusion principle. And this principle states that no two electrons within an atom can share the exact same set of 4 quantum numbers. So if you want to think of a set of quantum numbers as an address, it means that no two electrons within an atom can reside at the exact same address. Now, because of the spin limitation, that means that each orbital can hold only 2 electrons, because an orbital is defined by those first 3 quantum numbers, n, l, and m sub l. And then we have our spin quantum number, so an electron can share the first 3 of those, and then you can have a spin up and a spin down, and that's as different as you can possibly get. So if we look at something like helium here, if we look at the electron configuration for helium, it has 2 electrons. Both of those are going to go into a 1s orbital, and since I have 2 of them, I put them into there. And so we say this as 1s2, not 1s squared, 1s2. And we look at how we put them into the orbital diagram. We've got the spin up and the spin down there. So we've got both of our electrons in that 1s. And if we look at the set of quantum numbers, they both have an n equal 1 because they're in the 1s. L tells us we're in an s. An m sub l of 0, there's only one type of s, okay, because I can't go any farther with m sub l. It's plus or minus l, and since l is 0, I can only have an m sub l of 0. And the only possibilities I have for my electrons is that plus 1/2 and minus 1/2. There's no other way I can arrange these 4 quantum numbers and get any more electrons in there. So from this, we realize that each orbital can only hold 2 electrons. Well, that finishes out Lecture 9. It was a lot of difficult material, so if there's anything in there that you don't understand, please don't hesitate to get some help.